Okay, thanks. Everything seems to be working. So, hello, I'm Niko Anttiroiko from Finnish Heritage Agency that you might, okay, that you might know by the name of Museovirasto. It's, it's normally called. And I'm here to talk to you about our project, LiDAR, that stands for something like mapping archaeological heritage with AI and LiDAR data. And to present myself, my background is solidly in archaeology, so I'm not a machine learning guy in that sense. And I am the project manager in this project, so I'm trying to run things behind the scenes so that everything works. And it works. And to present this project or the outline of this project, our goal is primarily to develop methods for automatic detection of archaeological sites of different kinds using artificial intelligence and LiDAR 5 points data from the National Land Survey. And our project organization is as follows. So we have two main partners in this project. It's the Finnish Heritage Agency and then the University of Oulu. And both of us have primarily archaeologists working on the project. And then we have a variety of different partners with different roles in the project. So we have Blomkartta as our technical consultant that actually has been responsible for our method development. And then National Land Survey, they, of course, are the producer of much of the LiDAR data, and also the topographic database is one of the most important databases we use. Then we have Metsähallitus. They also have a huge interest in archaeological heritage in forested areas, and they have their own databases with lots of archaeological features. And then we have something called regional responsibility museums that are kind of the regional front line of archaeological heritage management that actually have to deal with the sites in real life. So they kind of do much of the footwork. And the funding for the project comes from the Minister of Agriculture and Forestry. So this is one of the kind of LiDAR 5P pilot projects they decided to fund. And I guess there are 3 other similar projects. And to continue, I could maybe talk a little about our use case. So currently there are about 68,000 known archaeological sites or features in our databases. And these include a wide variety of different things. Some might be protected by the law on archaeological heritage, and some are just some other culturally important objects we might be interested in or like to protect. And these sites are likely just the tip of the iceberg, really. So we estimate that there are more than 500,000 such sites in Finland, so most of those remain to be found. And the motivation for this is, of course, that the sites we don't know about, we can't protect or study in any way. And those are constantly at risk to get damaged by like forestry practices or land use, basically. And also, this kind of exposes the fact that the databases we currently have are not that accurate in spatial terms. So the spatial information is usually imprecise or in some cases just plain wrong. So we like to correct that if possible. And what's nice about the archaeological features is that many of those are easily detected in LiDAR data and have like visible features. And that makes it like a huge opportunity to apply AI or machine learning based methods to actually map those. And the picture on the right shows a really good example. These are tar kilns and charcoal kiln that are really nicely visible and have been mapped by our AI systems. Yes, and of course, not all of our archaeological features are suited for these kinds of studies. So we are only limited to those that exist in sufficiently large numbers, like thousands of sites, and those that are actually identifiable in really clear terms in LiDAR data. And to just show a couple of examples, the picture on top that might be a bit small, it shows a chain of hunting pits that are quite common in northern Finland. And those are one of the sites we've been studying in this project. Then the picture in the middle shows field fortifications from Eastern Finland from World War I era. We have a huge amount of those as well. And then the picture at the bottom shows some Bronze Age burial cairns that might be a little bit more difficult to see, but also interesting. So we are looking at these kinds of features and of course the tar kilns from previous slide. And the methods we use are actually pretty similar to some of the previous presentations. So we use a UNet-based image segmentation model. And of course, like the reason we are using this kind of method is that we are interested in like the areas that contain the sites. So we chose to use a image segmentation approach instead of like traditional object detection that might just detect the sites but not like outline the precise area. And also one of the like good things is that this model tends to perform pretty nicely on relatively small training data sets, and that's one of the problems we are kind of dealing with. There aren't that many known archaeological sites of given type, so we have to like make use of what we actually have. And our workflow looks something like this. So for LiDAR pre-processing, we use the same kind of topographic position index as Christian. The difference is that we use slightly smaller cell size, so we are actually upscaling or upsampling the LiDAR data to a higher extent. So we use 25 centimeters square size. We also made some tests with like Corsair model topographic position indexes, and we kind of lost around 10% of the detected features if we used 0.5 meter square size. Then we also do some other visualizations, mostly for visual use. So archaeologists have been using LiDAR for a long time, so most of us already have our favorite visualization we like to use for actually digitizing our training data sets. And for creating our training data sets, we have collected data from various registers and databases from Heritage Agency, Land Survey, and Metsähallitus. And then we have combined the features from those databases and digitized everything in there, and also digitized some new features, as usually there isn't quite enough features from the databases that exist. Then this machine learning part is fairly standard. I'll just move to verification. So we have done some automatic post-processing for the data by using a Python script that groups the detected features in like aggregate groups if they're really close to each other. That makes verification a bit faster. Then we calculate some attributes to help with the verification, like roundness, size, and so on. And we do most of the verification work just by looking at the data in GIS. And of course, if the cases are a bit unclear, we do also some field work. That's really limited. And after we are satisfied with the data we've produced, we process it for other uses, such as reusing it as part of another training data set, like adding it to the existing databases or research uses. And this all kind of require a bit different modifications to the data, and also might like need different levels of certainty that the features in the data are actually correct. And just to present our first case study in the project that acted as like pilot study inside a pilot study that was aimed at like getting our methods to work and like prove that the whole concept is viable. And we chose one research area in Kainuu, mostly based on that we knew that there are a lot of tar kilns that are one of the easiest archaeological objects there is to find and identifying LiDAR data. So we tried to make as simple use case as possible in this point. And we did this a couple of times over, improving our methods and training datasets as we progressed. And at around third iteration, we had something we were quite satisfied in. And just to show how this affected the situation of known sites and so on. So before our study, we knew around 800 tar kilns in the research area, and this number increased more than threefold after our project. And this is, I must note, an area where we actually knew really many tar kilns to begin with. So this is kind of the best case scenario for the existing databases. And what we were particularly impressed was that very few tar kilns that could be identified were actually missed. So currently we know of less than 50 cases where there probably is a tar kiln, but our model couldn't identify it. And to show something about the precision of the identifications and the limits of the sites identified by the model, we have an example of like a polygon from our training dataset on top left, and then some examples in red in other pictures that are polygons produced by our model, and these are pretty much spot on. And also, what's kind of evident in these pictures is that the model is also pretty good in finding damaged or partially destroyed features, like features that have been plowed over in forestry practices or so on. And that's something that's really important for us. The amount of false positives, of course, we have quite a lot, but that turned out to be manageable so that we can actually verify all the results by hand after this. And there's also actually an example of one of the false positives in the lower right corner. So the model seems to like ditches also and identifies those quite often as tar kilns. And after this initial pilot study, we've been trying to scale up the project. So we've applied the same to around 20 LiDAR 5 points production areas, and also some other types of archaeological features. So tar kilns and charcoal kilns were the two first ones, and probably the most simple. Pitfall trap systems, and then, of course, the World War era fortification systems. And also we are trying to add more types of sites as we go on, like Stone Age dwelling depressions that, just to tell you a little about what they are kind of remains of semi-subterranean dwellings from Stone Age. So that's something that we archaeologists are really interested in, and it would be really cool to actually venture into older and maybe more interesting features as we progress. And just to summarize some of the results so far, so we have been able to identify over 10,000 previously unknown cultural heritage sites so far, and this number is still increasing quite rapidly. And yeah, so far most of this increase comes from tar kilns, charcoal kilns, and so on. But we expect that we probably will find also thousands of like pitfall traps and fortification objects from World War I and II. And as we progress with more like identifiable features, the project also becomes slightly more challenging. So we already kind of exhausted the simplest and most easily identifiable features. And for example, like the Stone Age dwelling depressions I was speaking about you earlier, this picture here shows one example of such sites. You can't probably see my cursor, but there's like these small depressions visible in the hillshade that are quite easy to mix with natural depressions, and that makes detecting them with AI much more difficult than with the more clearly identifiable features. So this is something that we kind of consider possible, and we had some limited success, but this is probably something that we must be like prepared to accept, that the performance of the model will not be quite as high as with the more easily identifiable features, and the results will need much more verification in field. And to conclude, we've been really impressed with applying artificial intelligence to mapping archaeological features. We have produced unprecedented amount of data in this field. So after the project, I expect that 1 in 4 known archaeological features is something that we've identified in this project, which is quite impressive considering that we've been doing this for 150 years in this country. Also, the quality of the spatial data we produce is much better than has been previously possible, and this is going to change a lot of things in cultural heritage management field. And also, it's become evident that this amount of data we produce produces some challenges for the whole cultural heritage management sector in the future. One is that, of course, there is a huge amount of data, and some of the existing processes for protecting these sites are just not efficient enough at the moment. So we have to come up with new ideas how to actually manage and protect those sites. Also, we don't really have any guidelines for using the data produced by such methods. So we have to make sure that we actually start planning ahead and making sure that the guidelines are in place when this becomes even bigger than it already is. And also the current legislation that governs the cultural heritage management is quite old, and some changes might be in order to actually accommodate these kinds of methods in the future. And this process is also ongoing. I'm not quite sure what the results will be, but I hope they are for the better. And that was what I had to say. Thank you very much.